Ladies and gentlemen, in this session we are going to introduce practical assignment number 1, and here we are going to deal with topography, with maps and the 3D view of topographic maps, and we also are going to start introducing structural contours, strike lines, and simple geological contacts and simple geological situations inserted on topographic maps. Here on the left hand side we see a fairly simple topographic map with contour lines that are labeled according to the altitude along that line above sea level. You see it reaches here from about 300 to 330, 340, 350, 360 meters altitude. Well, this is a altitude that we see pretty commonly just south of Grahamstown, between Grahamstown and the coastline. Here on the right hand side we see a block diagram that shows this topography that is shown here only in 2 dimensions and topographic contour lines in a kind of a 3D view where we see high points, topographic high points, these summits of hills here and there and there and there. And we see here a valley that runs here from relatively low altitude to fairly high altitude over here. Here the valley splits up to the neck between these 2 hills. The hills themselves would be shown here as concentric rings that are cut off by the boundary of the map here, but normally these would be concentric rings of higher altitude where the terrain goes to a topographic maximum. Here on this topographic map we see contour lines 300 meters altitude, 310, 320 and so on towards the topographic high points at 370, 380 meters here and about 360 over here. The topographically lowest point is here at the southern end of the map in the valley, in that little river valley that we see here at something below 300 meters, but not as low as 290 because we don't see the 290 contour line. Everything along the yellow contour line that we see here is 300 meters above sea level. And here in the block diagram we see exactly this topographic feature here. In the valley along this line we have an altitude of 300 meters, but 300 meters altitude obviously does not only exist at the land surface, it also exists here in the subsurface. This topographic contour is a horizontal planar feature. It's an imaginary feature, obviously you will not see it in the field, but you can measure the altitude with a variety of devices. And wherever the topographic surface, the land surface is at 300 meters, you will find the 300 meter contour. At higher altitude, 310 meters, shown here in red, we see obviously the 310 meters contour cropping out at the surface along this line and then disappearing here in this block diagram into the subsurface, again forming a horizontal planar feature. On the map we only see here the 310 meter contour line. Obviously these contour lines continue, but the map simply ends here at a certain boundary. If you would have the neighboring map sheet, you can follow these contours to wherever the topography is at this respective altitude, 300 meters, 310 meters, or perhaps 320 meters here. We see here the 320 meter contour line covers a fairly large area of the map. This valley here is running from here the south to the north, almost to the northern end of this topographic map, and we see here everything between the red and the blue contour line has a topographic altitude between 310 and 320 meters above sea level. We also can see that here the distance between the 300 meter contour and the 310 meter contour is fairly narrow. Here you see between here and there is only a very small gap. That means that you don't have to walk far from the 300 meter contour up to the 310 meter contour, and that means the terrain is fairly steep here. If you change your altitude very quickly without walking very far, then you have a steeper terrain compared to, for instance, a situation here from the 310 meter contour, 310 meter altitude to 320 meter. So from here to here, you have to walk relatively far to gain 10 meters altitude. So the spacing of these contour lines will tell you something about the shape of the terrain, whether it is steep in areas where contour lines are narrowly spaced, or relatively shallow where they are widely spaced. And we see here this valley runs here fairly shallowly from 300 to 310 meters along the river, and then becomes even shallower between 310 and 320 meters, simply because the distance from here to there or here is further. Then again, going up these hills, and you see these hills, for instance, this slope here is going from relatively shallow to steeper and steeper and steeper, because you see here the contour lines, the 10-meter spaced contour lines, are getting narrower in position to each other. Now let's introduce some geology into topography. We have here another map, and here we see not only contour lines, they are not labeled here in this case, it's just an example for now. And we see that here the contour lines, they form again a valley. Here is a river, the valley splits here in this direction and this direction, and here is a third valley that splits over here. And we see here a hill with its typical concentric contour lines around the summit, and that is also shown here in the block diagram. Here is the hill with its summit, the hill with its summit, and here are the valleys, 1, 2, 3 little valleys. We see here 1, 2, 3 little valleys. Here is another ridge going down towards the river valley. That is the ridge here from over there. But in addition, we see geological information plotted into this block diagram or the topographic map on the left-hand side. This is a single planar interface. It is a contact between a rock of the layer A and a different rock of the layer B, and the contact between these two layers is a single planar interface, a single planar surface. And the position of this surface in the area is outlined here as a black line, and it's separating the dotted pattern from the clear pattern. In the block diagram, we see how that actually looks in 3 dimensions. You see here the contact of the two rocks, and obviously the contact of these two rocks is not horizontal. It is inclined. If it was horizontal, the contact would run parallel to some contour line. This contact is relatively shallowly dipping. It's dipping here somehow towards us. Let's have a look at differently oriented contacts between geological layers. Here we have seen a shallowly dipping contact. Let's look at this next map. It's the same terrain that we have seen before. Topography is identical, but now the contact between layer A and B has a different shape, and we see here it is running in a different fashion than we have seen before. Before, we have seen here strongly low-bayed shapes that were running in quite a long winding fashion across the topography. In this example here we see this is a less complex interface pattern. It runs up here, it runs down into the valley, and it runs up here, and this comes from the steepness of the interface. The steeper an interface, the more simple is the outcrop pattern on the surface. Here this moderately dipping contact will run up to the summit, into the valley, and onto the next hill in a fairly straightforward manner. Here, even steeper. You see now the contact between the two layers is a wavy line on the surface, and its dip angle, its orientation is very steep here between these two layers, the dotted and the clear layer. So this is a kind of a qualitative piece of information. The steeper a contact, the more simple is its outcrop pattern at the surface, irrespective of topography. Going back here, a very shallowly dipping contact has a kind of a fairly complex outcrop pattern that responds very strongly to topographic changes. Let's think about what if a contact was vertical. I'm pretty sure you can figure that out. If that contact here was vertical, the outcrop pattern of this contact on a topographic map would be a straight line. This contact here is not quite vertical, but almost, and that means its outcrop pattern is a little bit wavy, bending a little bit, responding to the valley and to the hill that it runs through here, but not very strongly, much less than the shallowly inclined contact. If the contact was horizontal, and we have mentioned that before, if it was horizontal, this contact would run parallel to any of these contour lines, depending on the altitude at which this contact happens to be. How can we determine strike and dip and the dip angle from geological maps? This is one of the main tasks set in the practical assignment today. Let's work with the moderately dipping contact that we have seen before. Here we see it's responding quite strongly to topography, and here we see it's moderately inclined and it has a planar shape. That means it's not buckled in any way or irregularly shaped. Let's assume this is a really planar boundary between two layers. Let's recap on the main terms that we need to work with this exercise today. The strike line is obviously a very important feature, and here we have an example of tilted, say, sedimentary beds, or they could be metamorphic layers, but we see here two different rock types interlayer to each other, and they are separated from each other by planar, uniformly oriented interfaces. A strike line on such an interface is always a horizontal line. The strike line, per definition, is a horizontal line on a geologically meaningful surface. And since we here have, say, sea level, see a little boat, we might be here at about 10 meters altitude. And that means this is the 10-meter strike line of this very interface. Of course, we can draw other strike lines. Here, for instance, the 5-meter strike line, and here the 0-meter strike line, and we could draw a -5 or a -10-meter strike line to indicate that these strike lines are here at sea level, or 5 meters or 10 meters above it, or perhaps even below sea level. There will be still strike lines. Important to mention is that a strike line has two ends, and when we look here at the compass direction, the strike of this surface here would be 40 degrees, which means it's almost northeast. The other end of the strike line obviously has a different azimuth, a different compass direction, and this compass direction is 40 plus 180 makes 220 degrees. So it's important to notice for any surface there are two strikes that describe the strike of such a planar surface. One end and another end of the strike line. Then there is a dip line. You see here that yellow line is the steepest possible line on this planar surface, on this bedding plane or interface of a metamorphic rock layer. And this dip line has an angle of 90 degrees with respect to the strike line measured on the surface. So from here on the surface to the dip line we will measure 90 degrees. Alternatively, from here to there we will measure 90 degrees. Down here we see a geological map of that area with the three layers that are cropping out here next to these lakes, to the sea, and we see here the strike line and the dip line. This is the symbol that you commonly use for indicating the strike and the dip direction, or the dip of a planar surface in the field. The 30 degrees here indicate how steep this layer happens to be oriented, and this is a dip angle of 30 degrees with respect to horizontal. Then there is the dip direction. The dip direction is an important quantity. We see here a horizontal line that is also at 90 degrees with respect to the strike line, but it is pointing not on the inclined surface. It is pointing horizontally like the strike lines. That means it's also a so-called azimuth, like the strike line here has an azimuth of 40 degrees, or 220 degrees in the opposite direction. The dip direction would be, in this case here, 40 degrees plus 90, 130 degrees. That is the dip direction of this surface. So the dip direction is always related by a right angle to the strike of the surface. But be careful, there is another possibility to use a right angle with respect to the strike line. You could measure from the end of this strike line here a clockwise 90 degrees angle, and you would arrive here at this direction, but this is a false dip direction. This dip direction points away from the real dip of this surface, which clearly dips here towards the right hand side of this block diagram. So what you have to do is you always have to look at the strike lines in terms of where are they going to lower topographic level. Here we have a strike line at 10 meters altitude, here at 5, and here at 0, and obviously this layer is dipping from the higher towards the lower strike line, and that would be obviously in this direction. So you always need to keep that in mind, that you label the strike lines properly on your structural maps when you determine the dip direction. The dip direction in there is then easy to find just at right angle with respect to the strike lines. So then we have the dip angle. We can call the dip angle alpha, and that is the angle between the dip line and the dip direction. We have here the dip line on the surface, and we have here the horizontal dip direction. The angle in between is, in this case, 30 degrees. That is the dip angle. So don't confuse dip direction, dip line, and dip angle. These are different things. On geological map, the dip direction is always parallel to the dip line symbol of such a planar surface. So now let's put that into kind of practical application and try to determine the strike and the dip angle and the dip direction for this planar interface that we have considered before, this moderately dipping interface. The first step that you take to construct strike lines is that you look at topographic contours. You label these topographic contours. Some of them always will be labeled on topographic maps. You have to have that piece of information. And here we see there are topographic contour lines of 300, 280, 260, 240 meters. Here's the 220, and here the 200 meter contour line. Above the 300 meter contour line, we see higher ones at 320 and 340 meters above sea level. Now this contact between our layers with a dotted pattern and the clear pattern runs up to this hill, and at this point here it intersects with the 280 meters contour. It also intersects with the 200 meters topographic contour at this place and at that place. In the block diagram we also can find these places here and there and there. At all these three places, the topographic contour of 200 meters intersects with the geological contact. And that means we can connect these points and identify a line where before erosion this contact would have been exposed, or a position where this contact will be exposed when, for instance, this part of the hill will be eroded down so that the topographic surface intersects with the contact between the two geological layers. We can do the same exercise here for the 260 meter contour. You see here the yellow intersections at this and that place. Or for the 240 meter contour. Here we see intersections between the contact there and there at 240 meters altitude in the field. So now we have a set of corresponding contour lines, and we just have to connect them with lines. This would be here the contact between layer A and layer B at 280s, at 260s, and at 240 meters, and you label these contacts accordingly. Contact between A and B at these different altitudes. Here we also see that this makes sense in 3 dimensions. So if we, for instance, stand at this position here, we are standing on the 300-meter topographic contour line, but we also are standing at the 280-meter structural contour, at the 280-meter strike line. That means at this position here, we could drill 20 meters vertically down and we would find the interface between these two rock layers. At the same time, for instance, at this position here, we are standing at the 240-meter topographic contour. We are also standing at the 280 meters structural contour or strike line. And that means that at this position here, we can drill how deep ever we like. We will never find an intersection between layers A and B because it has been eroded long before. The contact would have been 40 meters above our heads when we are standing at this 240-meter contour, because 280 meters is the structural contour. Now let's come to the calculation of the dip angle. Let's have a look. If we draw a line at right angle between the 280 meters contour from this position to the 240 meter contour at this position, we can measure the distance because we have here a scale. Here is a topographic map scale, 100 meters, that would be this distance, and this here is just half of it. That means from here to there it is a horizontal distance of 50 meters. We can show that also here in the block diagram. From here to here, a position above the 240 meter strike lines, that is 50 meters horizontal distance. The vertical distance is obviously calculated from the strike lines. Here it's a 280 meter strike line, here it's a 240 meter strike line. That means the vertical difference between these strike lines is 40 meters. And we can draw here a little triangle with 50 meters horizontal distance and 40 meters vertical distance. The tangent of alpha would be the difference in vertical altitude over the difference in horizontal altitude, or in this case here 40 meters over 50 meters. And with your calculator you will easily determine an angle of alpha, in this case of close to 39 degrees. That is essentially what you are doing in the exercise today. You will construct structural contours or strike lines, you will label them accordingly, you will measure the horizontal distance between them, and you will determine the vertical difference between the uppermost strike line that you can find and the lowermost strike line. You will do it this way because of accuracy reasons. And you will determine the dip angle of such simple geological contacts. So now, what would be the strike of the contact? The strike of the contact is simply the angle between topographic north and the strike line. And here we see topographic north, and the strike line happens to be measuring in a clockwise sense at 90 degrees with topographic north. And that means in our example, the strike is 90 degrees. Or if you want, 270 degrees if you measure all the way from north through east, south, until you hit the other end of the strike line over here. That would be 270 degrees. And that means the strike is east-west. So how to determine the dip direction? The dip direction is easily determined at right angle with respect to the strike line, and always pointing from the highest strike line to the lowest strike line, in this case here from 280 towards 240 meters. This is this direction. The dip is in this case south. If we have an east-west strike, we have either a northern or a southern dip. And if our strike lines are arranged in a way that in the north there are the higher ones and in the south there are the lower ones, then obviously the layer is dipping to the south. As we see here, this interface is dipping to a southern direction. That's actually all you have to do for this kind of exercise. Just be conscientious about it, and the best way is obviously to understand that and not to follow a kind of tick box or rote learned procedure. If you know what you're doing, you will be able to construct such strike lines for any planar contact, provided that you have a topographic map and the scale and the north direction. That's all you need. Thank you very much.